multiplying and dividing radicals and rationalize the radical. Product rule gives us a technique on how to multiply two radicals. So say if given two radicals with the same indices, which means that if the roots are the same, let me change that to n, then we can multiply them together by combining them under just one radical with the same index or root, and then multiply them together. So let's take a look at some of the examples that we can use to apply this product rule to multiply two radicals. Notice that these two radicals, they have the same roots. The root here is a 2 and the root here is also a 2. When it is not written, it is a 2. So according to the product rule, yes, we can multiply them together, which becomes, that's a 10, which becomes the square root of 50, okay? And then from here, then we can now remove any number that's a perfect square from 50. So what we do is we factor 50, and 50 can be written as 25 times 2. And because 25 is a perfect square, that becomes a 5 on the outside. So we go, that's 5, the square root of 2, and we're done. There are two radicals in here, so let's go ahead and simplify this by applying the product rule if we can. So first we see two radicals, but we also see numbers outside the radicals. So we separate the numbers outside the radicals, and then we separate the two radicals side by side. Multiplying these together gives us 6, and then applying the rule for product of two radicals gives us one radical with 6 and 3 right below it. So when we multiply the two numbers together, we get 18. Now, don't forget about the list of perfect square numbers, which are these, and so on and so forth, right? So ask yourself, what is the smallest perfect square? What is the largest perfect square that goes into 18? Well, it turns out that 9 does go into 18, so therefore, we will rewrite 18 as 9 times 2, because 9 times 2 is 18. Now, 9 is a perfect square, so we're going to go ahead and pull out a 3. We pull out a 3, and then 6 times 3 is 18, so therefore, our final answer for number 2 is 18 root 2. We're going to continue to use the product rule to simplify radicals, but in the next 5 problems, we're going to go backward. So given a product of two numbers, we can actually separate them into two radicals, and that's also true for the product rule. So if we look at problem number 4, which says that you got 98, then to simplify this, we can use the product rule strategy, which means that we look for two numbers whose product is 98, but hopefully one of them is going to be a perfect square. So if we continue down this list, the next one's going to be 36, 49, 64. These are all perfect squares. So in order to use the product rule to help simplify radicals, what we're going to do is we're going to take the given number and we're going to ask ourselves, what is the largest perfect square that will divide into 98? Turns out that 49 does divide into 98. So therefore, we can write 98 as 49 times 2. And then using this rule allows us to split them up into two radicals. So therefore, we're going to write it as radical 49 times radical 2. And therefore, we get 7 root 2. All right. The cube root of 25 times the cube root of 10. So using the product rule, because the two roots or the indexes are the same, we will now combine them under one big radical with the same root, which is 3. So then you have 25 times 10. And now, you multiply them together, you get 250. Okay? And we are going to search through the cube roots. So if you look at some of the perfect cubes, they start at 1, followed by 8, followed by 27, followed by 64, followed by 125, and so on and so forth. So these are some of the perfect cubes, and it turns out that 125 does divide into 250, and therefore we're going to write 250 as 125 times 2. Alright, so 125 is a perfect cube. That means that we can actually take out a 5. So 5 can go, and therefore you have a cube root of 2 left inside for your problem. Slide over to number 6. We're going to again use the product rule, either this direction or that direction, to simplify our radical. So I'm looking for the square root, and the first number that I notice is the number 8. And 8 is not a perfect square. So what I want to do is I want to separate 8. I want to put anything that's a perfect square in the first radical and anything that's not a perfect square in the second radical. So for 8, notice that 8 is 4 times 2. And 4 is a perfect square. So I'm going to put 4 in here, and I'm going to put 2 in there. For the m to the 4th, m to the 4th is actually a perfect square. So I'm going to put m to the 4th here. And then n is not a perfect square, so that goes out there. So when we simplify the first radical, we get 2 for the 4. And then for the m to the 4th, we actually get m squared, because m squared gives you m to the 4th. So that's why we get that. Now in the second radical, there's nothing we can do, so we leave it alone. And that's the best we can do. Okay, slide over here. 36w to the 3rd. We are going to separate them into 2 radicals. 36 is a perfect square, so we put it there. Now for w to the 3rd, that can be separated into w squared times w, because that's w to the 3rd. And I put w squared because w squared is a perfect square. So when we simplify, we get 6w times root w. We're done. Multiply these two. So one thing to always keep in mind is make sure you check the roots, the indices, to make sure they're the same before you multiply. And if they are, then we go ahead and we put them under one big radicals. Now I see the 2 9s, so I'm going to put them next to each other. I also see the 2 x's, so I'm going to put them next to each other. And so with the y's, this becomes 81, x to the 7, y to the 9. And now I split them up again. Anything that's a perfect square or perfect cube in this case goes in the first radical, and anything that's not goes in the second radical. So if we think about it, the 81 is 27 times 3, and 27 is a perfect cube, so that's why I put it in there. X to the 7, so x to the 7, start with the smallest one, which is x to the 3rd, and then multiples of that would be x to the 6th. So for x to the 7, technically you can actually group 2 groups of x to the 3rd. That leaves you with x to the 6th, and then you're left with just 1x. That makes it x to the 7. For the y to the 9, that's actually a perfect cube because 9 is a multiple of 3. 6 is a multiple of 3, right? But we have 1 left, which is 7. That's why we put that 1 there. So by looking at the first radical, we know that that becomes 3x squared y to the 3rd, because you have 2x cubes here, you have 3y cubes here, so that's why you're able to take that out. And then inside this radical, that's the best you can do. So there you go. Now we apply the quotient rule to radicals to simplify radicals. Very similar to the product rule, the quotient rule says that whenever you divide two radicals with the same indices or same root, you can combine them under one big radical with the same index. So then you have the big radical of A over B. Now that's helpful because we can also go backward to separate them as well, especially when we're simplifying a radical. So if I want to simplify this radical, then what I have to do is I have to go from this step to separate them into two radicals, and then I'll simplify them. So here's what I mean. This becomes the square root of 49 over the square root of x to the fourth. Square root of x to the fourth is 7. The square root of 49 is x squared because there are two sets of x squares in x to the fourth. And we're done. Same thing to this problem. This is a cube root, so make sure you write the number 3 there. 54m to the fourth over the cube root of n to the third. Okay? So here, we're going to apply the product rule to kind of separate the two. Okay, 54 is 27 times 2. That's 54. Now, why 27? Well, because 27 is a perfect cube. So that's why you have to memorize the first 10 perfect cubes, maybe the first 6 perfect cubes, and the first 12 perfect squares. And then over here, this is just going to be, let's take care of the m to the fourth. We want to look for multiples of 3 of m, so you get m to the third times m. And then over here, this guy, I guess you can just simplify it quickly because that's just n. So then at the end of the day, you have 3m times the cube root of 2m over n. And that's it. All right, simplify this. Now, we want to use the quotient rule going from this direction to that direction so that we can combine this under one radical. So applying the quotient rule gives us 48 over 3, and that brings it to 3 goes into 48. 3 goes into 4 one time with the remainder of 1, and then you have 3, and then you have 18 left. So if you take 18 and divide that by 3, you get 6. And that becomes 4, because the square root of 16 is 4. Let's move to number 11. Take these two and combine them together using this rule. Now notice that this is the only number that's outside the radical, so when you combine them, that's the only one that stays outside the radical, which I will write it as 1 over 2 because that 2 is in the denominator. And then look, and then I put everything else in the radical like that. So then I have 1 over 2. If you divide, you get 8. If you divide here, you get x to the third. And then you also have y to the fifth. Okay. So to make a long problem short, we know that the cube root of 8 is 2, so that comes out. The cube root of x cubed is x. Now y to the fifth means that you have one multiple of y to the third. So you can take out y, and then you're going to have a y squared inside. And that's all you can do. And then you would simplify here a little bit. So then you have x, y, cube root of y squared, and you're done. All right, so what we want to do is we want to know how can we remove the radicals in the denominator. Because when we one of the conditions to simplify radicals is to no longer have any radicals in the denominator. So what we're going to do is we're going to rationalize it. It means to get rid of the radical by multiplying the expression by 1. So here's what I mean. The first thing you're going to do is you're going to apply the quotient rule to write it like this. Okay? And it turns out that if you multiply this expression by 1, then you can get rid of any radical in the denominator. So what do I mean by multiplying it by 1? Well, 1 can be expressed in many different ways, but one way is to write it as root 3 over root 3. That's 1. But if we do it this way, then we no longer have any radical in the denominator, because if you think about it, this becomes root 9, because we can multiply those together, and this becomes root 15. Okay. And root 9 is 3. So there's no longer any radical in the denominator. So what's the trick here? Well, the trick here is you try to multiply this number by another number that makes it a perfect square. Now most of the times it will be itself, but sometimes it might not be. So you kind of have to be careful, okay? Let's go on to the next problem, number 13. I have 4, I have cube root of c down here, but I want to get rid of the radical in the denominator. So I'm going to do a trick. I'm going to try to remove the radical in the denominator by multiplying it by top and bottom by the cube root of c squared. The reason why c squared is because c squared and 1c makes it c to the third. And you know that c to the third means that that is going to go away. So then this becomes a c now, and then you have 4 the cube root of c to the second, and you're done. Let's take a look at number 14. I'm going to apply the quotient rule by splitting it up into the cube root of 3 over the cube root of 8. All right? Now, you have a few options here, but one thing I would do is because 4 goes into 8, and 4 is a perfect square, turns out that I can write the number 8 as that, which allows us to pull out a 2 from the 4. And then we have a root 2 down here. So now here's where we do our work to try to get rid of the radical of 2. We do that by multiplying the top and bottom by rad 2 over rad 2. This gives us rad 6 if you multiply them together. And this gives us 2 rad 4. And rad 4, it's actually another number 2. So therefore, we get rad 6 over 4. All right, we're on to our last problem now. We got this situation here where we want to get rid of our denominator. We want to get rid of the radical in the denominator. So what I'm going to do is I'm going to multiply the top and bottom by the same radical. Okay, but you got to be creative here. So ask yourself, what is the smallest perfect cube that 4 actually will go into? And it turns out that 4 goes into 8. And 8 is the next perfect cube. So then how do I make 4 into an 8? Well, I need to multiply that by 2. If I see an exponent of 1, then I'm going to need 2 more in order for me to remove that base from the radical. So therefore, I'm going to need an x squared. And notice that I don't really need to do anything to the y because y is raised to the third power. So in this case, y is raised to the second. So I do need to do something. So that means that I need 1 extra y to make it y to the third. Now, whatever I came up with in the denominator, I'm going to write that in the numerator. And now I'm going to simplify. For the numerator, this is what I get. For the denominator, if I multiply these together, I'm going to get the cube root of 8, because you multiply those together, x cubed y cubed, and that becomes 3y 2x squared y all over 2xy. The y are going to cancel out, and therefore you have everything over 2x.